All right, so it's the pleasure to introduce the last speaker for this morning and for the conference, Yael Karshon from Tel Aviv and University of Toronto. Will speak about geometric quantization of Lagrangian torus fibrations.
Thank you, Eckhart, because I'm the last speaker. Oh, first of all, just stay tuned. After my talk, there will be a couple of announcements by Eckhart, Anton, and Chen Chang. And so make sure you stick around for those announcements. And before I begin, because I'm the last speaker, I think this is an opportunity to say a lot of thank yous to a lot of people. Maybe I'll start with the scientific committee. Anton Alexev, Henrik Burstein, Rui Fernandez, Juan Huelu, Eckhart Meinreichen, and Changchang Zhou. So. I will go ahead and mention the people that worked very hard on the local organizing committee, or at least mostly local. Mario, and I apologize for possibly mispronouncing, Mario Garcia Fernandez, David Iglesias Ponte, David Martin de Diego, Anastasia Matveva, Eva Miranda, Cedric Oms, Danielle Peralta Salas, and Roberto Rubio. And maybe just to single out, maybe I should really single out Eva. Again, I don't know much of the behind the scenes, but at least for me, Eva's energy seems absolutely central to this event, and she's been just amazing. And kind of sorry she can't be with us at the very end of the conference, but I'd like to sort of make a particular acknowledgement of her contribution. So I begin with my talk, and I've added a subtitle. My title is Geometric Quantization of Lagrangian Torus Fibrations, and I've added a subtitle, Effect about Integral Affine Geometry. And what I forgot to put in my abstract is that this is not work on my own. This is quite joint with two people. Mark Hamilton, there's two mathematicians by this first and last name. So this is the Canadian Mark Hamilton from Mount Allison University, and Takahiko Yoshida from Meiji University in Japan. In particular, the phrase integral affine geometry, I think Mark Hamilton brought it up, and I will explain. And before I even begin, maybe I'll sort of, give the punchline to the experts. So the motivation here is the invariance of polarization phenomena and geometric quantization. Geometric quantization is basically a collection of recipes. You start with a symplectic manifold. You might need some sort of integrality condition, quantization condition. You think of the symplectic manifold as a classical mechanical system, symplectic manifold models, phase space, and you're trying to come up with a recipe that will give rise to a Hilbert space or some kind of a quantum space. You might want to do this in the presence of symmetries, Lie group symmetries, possibly Lie algebra symmetries. These are a sub-algebra of the Poisson algebra. You might want to do the whole Poisson algebra, go from smooth functions to operators, a lot of different recipes. And one of the phenomena that you see in geometric quantization, which is still mysterious to some extent, there's versions of the recipe that involves choices, and in a lot of cases the answer turns out to be independent of the choices, and sometimes this is not always understood, and this is a very central theme in geometric quantization. And what we're looking at is a situation of a compact symplectic manifold that comes equipped with a Lagrangian torus fibration over another manifold of half the dimension, so you can think of it as a completely integrable system. This is an on-to-God fibration, not a singular fibration. And in this situation, there's two things you can do, so I will explain more, but just for the expert. One of them is there's some index theoretic version of quantization, but people have explained in this conference, And the dimension of the resulting Hilbert space, or, well, maybe you should say virtual space, the dimension is given by the Riemann-Roch number of the symplectic manifold. So that would be one version of quantization. There's a different version of quantization. The first one did not make use of the Lagrangian torus fibration. The second one does. In the second one, you would be counting the number of Bohr-Sommerfeld leaves, for those who are familiar with this term. And these two recipes turn out to give the same answer. And this is the sort of the punchline of this talk. Now, I tell my students to not be apologetic when they give talks, but I will be apologetic in two opposite ways. One of them, this theorem I've just verbally described, you can actually find it in a paper from 25 years ago by Jürgen Andersen. And there's several reasons why we are actually doing this project. First of all, that paper does a lot more, and we're trying to say something very, very easy that can be extracted and said directly in a very direct way. Second, Andersen does have some assumptions that we believe are not always true, so we prove it in a bigger generality, like in the full generality. In fact, our collaborator Takahiko Yoshida also has a paper that removes these assumptions, these extra assumptions, but we're doing something easier. I think sometimes there's value of showing when something is easy, sort of doing it and extracting it from the more complicated context. And a third reason is Andersen's paper, there's pieces there that we view as gaps, maybe. You know, they were correct, but it took some sweat to justify them. So, you know, so definitely we can give Andersen credit for this, but I think it was worth actually spelling it out and making it explicit and showing it in an easy way. So that's one side of apologizing, which is, oh, this is known since 25 years ago. Another side of apologizing is we haven't written out everything, so, oh, maybe I'm going to say something that is wrong. It happens when you haven't finished writing. So it's an easy, again, I can give you the whole argument depending on times, but, you know, who knows until you actually publish. Even when you publish it, it's never 100% true. So, you know, that's the second apology. Let me do the... So maybe I'll actually, I think I'm going to spend most of the talk about integral affine geometry. Maybe I'll spend most of it about this. So we're looking at affine maps from Rn to Rn. X goes to Ax plus B, where A is an n by n matrix, B is a vector in Rn. This is a definition of an affine map. And then there are special cases. An integral affine map is when the linearization is in GLN Z, and by n matrices with integer coefficients whose inverse has the same form. That's the same as saying the determinant is plus or minus 1. And this is the same as saying that the linearization preserves the standard lattice Zn. Then there's a stronger condition called, we call it integral affine, where not only the linearization, but also the map itself preserves the lattice Zn.
Sorry, just for clarity, if Cn becomes Qn, would you call it integral rational or rational integral?
Well, you know, my colleague in Tel Aviv, Vitaly Meilman, once told me, you know, one should be very cautious, not to be meant to be offensive, but not to pollute mathematics with terminology. So if you know, I would be cautious to not declare names about objects that I'm not actually using. This said, I think that your question is not about terminology, but about ideology. Can you repeat the question?
If Cn becomes Qn,
right.
Call it integral rational or rational integral?
So what would the condition be? Are you requiring the linearization to preserve Qn or the map itself to, like, what is the condition? Because there's two things here. There's property of the linearization, and then there's a stronger property of the actual map, right? So the question is, what is the requirement that you're making? So it would depend on the actual requirement. One can think of different options. And then, of course, you can talk about manifolds corresponding to this structure. So an integral affine manifold is a manifold equipped with a maximal integral affine atlas, by which we mean an atlas whose transition maps are locally integral affine. An integral affine manifold comes equipped with a maximal integral affine atlas. So this is a stricter requirement that the transition maps are locally integral affine. So if you have an affine structure, let me sort of put some color here, that gives rise to a flat torsion-free connection of the tangent bundle. You just get it from the charts, and it is consistent on overlaps. If you have an integral affine structure, you get more. At each point, you have an integral lattice in the tangent space to that point, and the period lattice, that's a dual lattice in the cotangent space to that point. And again, these just come from Z, from the charts, just from. But in particular, what these give you is a well-defined measure, smooth measure on your manifold. And if you have the strongest condition, then you actually have inside your manifold a good notion of integer points, not just in the tangent spaces, but in the manifold itself. So you have lattice points in the manifold itself. And my subtitle was about a fact in integral affine geometry, and this fact is if the manifold is compact, then the number of integer points is equal to the volume. And if you think about it, it's supposed to be obvious, right? Because the integer, up to maybe factors of 2 pi, there might be some conventions there. But, the points are sort of evenly spaced, if everything's compact. Like, you don't expect to have any boundary terms. So this is very, very natural. You're expecting this to be obvious. And when we came about to prove that, find that easy proof of that phenomena, invariance of polarization phenomena and geometric quantization, it turned out to boil down to this fact. And yes, of course, this fact is obvious, right? And then we got stuck in proving it. And it turns out that, yes, Anton.
Sorry, what kind of volume? The natural volume in your charts?
The volume comes from the charts, from the smooth measure in Rn, yeah. So we actually got stuck in proving this, and it turns out that this has sort of also interesting connection with some looping problem. But finally for a while we were thinking of reversing the story because this invariance of polarization, we sort of already know it from these other people's papers. So we're thinking of, maybe we can use that to prove this simple fact from integral affine geometry, which would have been kind of outrageous. But this simple fact is if eventually it's fine, we can prove it. I'll show you how to do it. You do use some geometry. You don't need as much as quantization. You do need Lagrangian torus fibrations to prove it. So I will show you the proof of this fact. And let's do some examples of integral affine manifolds. The main examples would be coming from quotients of Rn by some group. And the group will be a group of integral affine, or maybe integral affine transformations acting freely and properly on Rn. So then you can take the quotient that has the required structure. So of course we can have the torus, we can have the Klein bottle. So I think it was Daniela Seppe's early papers was explaining about Lagrangian torus fibrations where the basis is a Klein bottle. We've got manifolds of the type of Kodaira-Thurston, and you can come up with more things. But what turns out to be, to my understanding, open and actually connected with a famous problem called Marcus conjecture in affine geometry is, let me phrase our version of the question. Suppose that you're given an integral affine, you know what, I don't even need it, I don't need, just do one of them, okay? Integral affine manifold, which is compact, can it always does it always come from Rn? So locally it comes from Rn because of the charts, and you can sort of do the developing map, it gives you a local diffeomorphism from the universal covering to Rn, which induces the integral affine structure. But then the question is, this map from the universal covering to Rn, is it going to be onto, example? So that's sort of a kind of, we don't know any counterexamples. So that's one of the tricky things. One thing I should mention, like as you see, these manifolds do not need to be oriented, but for the purpose, orientable even, but for the purpose of our fact, integer points equals volume, that's not a big deal. You can always pass to a double covering that is oriented, and the number of integer points will double, and the volume will double. So that's not a big deal. Now, these integral affine manifolds come about from proper Lagrangian fibrations. And again, this is classical. If you have a proper Lagrangian, so symplectic manifold equipped with a proper map to another manifold, and that map is a fibration, and the fibers are Lagrangian. And under these assumptions, we have the Arnold-Liouville theorem. In fact, Arnold-Liouville is more general because it does not require the map to be proper, but I will focus on the case of a proper map. And in that case, Arnold-Liouville theorem tells you that you can actually find semi-local coordinates. Semi-local means pre-image of an open set in B. So it's not kind of not a tiny thing in M, but in fact a pre-image of an open set in B. And we call these Arnold-Liouville charts, the coordinates coming from the Arnold-Liouville action angle variables. So near each point of B, you can find coordinates x1 through xn, and in the pre-image, you can extend these to coordinates of the manifold itself such that the two-form becomes standard. And if you take these Arnold-Liouville charts and you cover your manifold with them, you can then focus attention on the xn's. That gives you an atlas of B, and turns out that the condition for the upstairs to be Arnold-Liouville forces the downstairs to give you an integral affine atlas on B. So if you have a proper Lagrangian fibration, the base acquires an integral affine structure. Again, this is sort of classical. Okay? And yeah, we want to do this in the presence. So we will want to do this in the presence of quantization. So proper Lagrangian fibration will give you an integral affine structure. If you pre-quantize, you will get an integral affine structure. So let me show that. So here's the pre-quantization. So now we have a tower on top of the, we have the Lagrangian torus fibration. On top of that, we have a so-called pre-quantization line bundle. This is a complex line bundle equipped with a Hermitian structure and a connection that preserves the Hermitian structure, and whose curvature is the two-form. And I am suppressing some factors of like I over 2 pi, depending on conventions. And this allows us to obtain enhanced Arnold-Liouville charts, where you're not just taking it, you're taking a pre-image of a little open set in B, pre-image in this tower. You will find local trivializations of your line bundle over these open sets, such that the connection has a very specific formula. And these enhanced Arnold-Liouville charts will give rise to an integral affine atlas downstairs. So in the presence of a pre-quantization, you actually have more structure downstairs. So I want to tell you something about this fact from integral affine geometry. And I explained that this integral affine geometry comes from Lagrangian torus fibrations that are pre-quantized. But now we do the other way around, because we want to prove something about integral affine manifolds. We're going to reverse it. We're going to start with the integral affine manifold or integral, and we're going to build a Lagrangian torus fibration. So again, this is fairly standard. You're given your B, you're taking the cotangent bundle, the integral affine structure gives rise to a period lattice. You take the fiber-wise quotient, that's a torus bundle. It is a Lagrangian torus bundle. Interestingly speaking, if you started with a Lagrangian torus fibration, then you take the integral affine structure on the base, and then you apply this recipe, you might not get back the original manifold you had. There might be certain twisting, something that Dustrumat refers to as like kind of Dustrumat first term class. But that's okay. For our purpose, we just need these ones which are untwisted. And then you can take the dual torus fibration that is just a tangent bundle modded out by the integral lattice. And here again, we have semi-local coordinates. You're taking on the base integral local coordinates coming from the integral affine structure. You have adapted coordinates in the tangent bundle, and modulo 1 gives you adapted coordinates in M check in this dual torus bundle. Now, one interesting thing about these guys is each fiber is a torus, an actual torus. It has an identity because we have a zero section in tangent and cotangent bundle. So each one is actually torus, and then the torus is also acting on the fiber for abelian transitively, just acting on itself. If you go to M naught, if you started with an M, then take a B, then take M naught, the original M might not have a zero section. That's a twistedness. The fibers of M naught, these are tori. Each of them acts freely and transitively at the corresponding fiber of M. But I will focus on M check. So these tori, these are n-dimensional tori, but as you go around a non-trivial loop in the homotopy of B, you might come back to your torus with an automorphism. And this is exactly an expression of Dustrumat's monodromy. So we've got these local torus actions on preimages of open subsets of small enough open subsets of B. You will have a torus action, but on overlaps, these torus actions will differ by automorphisms of the torus. So this is sort of an interesting structure. It's not quite a torus action, it's a local torus action. And that's part of the challenge here. So let me give you some relevant ingredients. What does the local torus action? So here are some technical stuff that we will need to prove this fact about integral affine geometry. I think so far I'm just doing integral affine. So no lattice points at this point yet. So we've got this local torus action, which on overlaps differs by automorphism of the torus, but the notion for what does it mean for a differential form to be invariant, that notion is well defined. So if you have an invariant form, you can examine invariance with respect to these open sets where you have an honest-to-God torus action, but you apply an automorphism of the torus, that's still invariant. So the notion of invariant differential form is well defined. And invariant differential form gives us a subcomplex of the Ram complex. So we can take the cohomology of that subcomplex, we get the cohomology of the complex of invariant differential forms. And we've got a map from that cohomology to the ordinary de Rham cohomology of our manifold. And the crucial lemma that we need is that this map is an isomorphism. Now, if we only have a torus section, we would know how to do that. If you only have a torus section, we have it's fairly straightforward to just give an inverse of this map. You have a differential form, you average. Because the torus was, is connected, you're taking an average of differential forms, which are all in the same cohomology class. So the average is in the same cohomology class. And the averaging map gives you an inverse to the inclusion map in cohomology. So in the case of a torus action, cohomology is represented by invariant differential form. And then the question is, what happens when you have a local torus action? When you play this game, for torus local torus action, you can still average. And the reason is you can average locally, and when you average, what kind of appears there is the Haar measure of the torus, and that's invariant under automorphisms of the torus. So when you average, that is well defined. But the question is, when you average, do you get the same cohomology class that you started with? So that's not totally obvious. So let's explain why this is true. Well, we're doing it for local torus actions where the manifold is covered by finitely many invariant open sets where the action is a genuine torus action. But in our case, it's okay that manifold is compact. And then we do induction on the number of such open sets where you have a genuine torus action. So if it's just one of them, I explained. You can guess.
I think this looks difficult because he insists on using group actions and have an action of a groupoid.
Yes, yes. You could, in our particular situation, you can rephrase the action in the language of Lie groupoid, and maybe we can talk afterwards if you have another way of, like, again, we need something very specific. We need the cohomology, every cohomology class to be represented by an invariant form. So if, then we should talk afterwards, yeah. But, so let me show you what it is in our case. So in our case, we do use finiteness of the cover, and basically it's a Meyer-Torus argument. So if you write down, if you add pieces of the cover one by one, then at each stage you're applying an induction hypothesis and just, write down the relevant Meyer-Torus sequence and apply the 5 lemma. The assumption of the 5 lemma will be guaranteed by the induction hypothesis. So this is sort of the little argument that by which we show that inclusion map really does give us an isomorphism cohomology from the cohomology of the complex of invariant forms to the ordinary normal cohomology, and kind of look forward to hear from Marius the more general thing that we might be able to just quote here. Because if you first include and then average, starting with an invariant form, you didn't do anything. So we do know that the average map provides us with a left inverse to the inclusion map. So as soon as we know that the inclusion map is an isomorphism, we know that the average map is also a right inverse. So we have a left and right inverse. Okay. So that's a little bit technical. Now, what do we do with this? Why do we want this? So let me give you another little technical thing. So this is I'm still with the integral affine. I don't need yet integral affine. So remind you the setup. We've got an integral affine manifold. We've got the integral lattice and the tangent bundle. We've got the M check, is just obtained by fiberized quotient by the integral lattice. We've got the adapted coordinates. And we have a well-defined zero section. And I will assume that the B is oriented, otherwise I pass to double covering, and that's good enough for me. So in these adapted coordinates, first of all, we notice that if you take the dy1, wedge dy2, etc., where the y's are just the fiber coordinates, that is independent of the choice of adapted coordinates, because the axes, they came from integral affine atlas. So transition map will be integral affine, and these guys have determinant 1. And the transition map on the y's, will have determinant 1. So y dy1, wedge dy2, etc., that this is actually well defined. And this is a closed end form, so then you can take its cohomology class, and one wants to claim that this is the Poisson dual of the zero section. And if you sort of stare at it long enough, it's like, oh, it's sort of obvious. To prove it, we do need what I mentioned before, the fact that each cohomology class has an invariant representative. We do use that to prove this Poisson dual description. So what is it that let me actually copy the, this is what we're trying to prove. And what is that we want to prove? We want to prove that if you take the zero section and you integrate a differential form of degree n, that's the same thing as wedging with a dy1 through dyn and integrating over the whole manifold. Now, we already know by the previous argument that the differential form has an invariant, its cohomology class has an invariant representative. So locally, this is what the invariant representative looks like. It only has axes because the local torus action moves in the y direction. And I guess if you did have any dy's, then this integral will just give you 0. So if this integral has a chance of being non-zero, then your form locally can be written as a function times dx1 wedge dot 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 wedge dxn. And then you just follow your nose. You write your integral on the 0 section as the integral of this particular form. Yeah, strictly speaking, maybe I'm actually using local coordinates and patching by partitions of unity. By Fubini's theorem, you can just express it as an integral of the whole manifold, and there you go. Okay, so what did I just prove? I proved we have a particular formula for the Poincaré dual of the 0 section. Now, what is our goal? Our goal is to prove this little fact from integral into affine geometry. Now I am going to be doing integral affine. So in this case, we have not only the 0 section, but we also have the diagonal section. Integral affine means that it makes sense to require the y coordinates to be given by the x coordinates modulo 1. And that's sort of a well-defined condition. So we have a well-defined diagonal section. And the integral set is exactly, in fact, let me actually do this. Integral set consists of those x's such that, how should I say this? X day mod 1 is equal to 0, right? I mean, okay, maybe I'll write it this way. So this is just given by the intersection of the 0 section with the diagonal. So now let's finally prove this fact about integral affine geometry. So we're looking at the number of lattice points. That's the same as the magnitude of the intersection of the 0 section with the diagonal section. And one can actually check if you follow the conventions that all the intersections contribute the same sign. Because dy1 wedge dot 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 wedge dyn was the Poincaré dual of the 0 section, we can express this as the integral over d of this differential form, dy1 wedge dot 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 wedge dyn. But then think of d as just it's a section, so we can pull it back to the base. So this is the same as integrating over b, but then we need to, when you pull back the dy's, because of the condition that defined b, the wedge of the dy's pulls back to the wedge of the dx's, and we just get the volume of b. So it's a kind of, you just follow your nose, you get what you wanted. And this completes the proof of this fact from integral affine geometry. So now we want to use that fact to, yes?
M hat has a complex structure.
I'm sorry?
M hat has a complex structure.
Are you asking or saying?
I'm saying. I'm wondering how your that doesn't come into play.
It will in a second. But actually, I'm going to choose any, but I'm not going to refer to a specific, actually, no, I lied to you. No, I lied to you. No, I do not know how it connects, how it can be used here. So, yeah, here I'm not using complex structure. But let's move on to, I think, but again, I don't know. I mean, this can be an interesting feature. Let's now look at the question about quantization. So M hat was a quotient of the tangent bundle. I'm sorry, M check was a quotient of the tangent bundle. M naught was a quotient of the cotangent. But I don't want even M naught. I want the thing on which M naught is acting. I want to go back to the very original Lagrangian torus fibration that we started out with. And now I'm going to describe to you two versions of quantization. I already said what pre-quantization is. So we have a tower. And the one version of quantization is the Bohr-Sommerfeld recipe. Because the curvature of the line bundle is the two form and the fibers are Lagrangian, that means that the line bundle is flat over the fibers. So over the fibers of our Lagrangian torus fibration, of each fiber we have a flat complex line bundle, and you can ask, is that flat line bundle trivial or not? Is the connection trivial? And those fibers for which the connection is trivial, these are by definition the Bohr-Sommerfeld fibers. And it turns out to be a discrete, they form a discrete set inside the base B, and one can define, one of the possible recipes you can take is for your quantization, at least a Hilbert space, to have one generated for each Bohr-Sommerfeld fiber. And that's one possible recipe, and I'm doing a lot of, okay. So this is a quantization recipe where the dimension of the Hilbert space is just the number of Bohr-Sommerfeld fibers, and did I write this down even? Maybe I forgot to write this down. I think I forgot to write this down. Okay, so let me say something about this. Fact. Oh, here we go. I did write it down. If you sort of follow, look what happens in local coordinates, you're going to find out that a fiber is Bohr-Sommerfeld exactly if the corresponding point of B is an integral point for the induced integral affine structure. So this Hilbert space, its dimension is just the number of lattice points in the base. Now let's go to the second of the two quantization recipes. This is Dirac-Dolbeau quantization. I use a different name for this. A lot of people call this spin C. For me, spin C is a slightly different recipe, so that in some sense incorporates the half-form correction. So I'm not talking about this today, but I am sort of cautious about my terminology. I do insist to call this Dirac-Dolbeau rather than spin C. We do expect everything that we do to also work in the spin C case, in which case instead of the Todd class, you're going to have the A roof class, but everything should work just as is. In this case, one cooks up a Hilbert space or vector space or possibly a virtual vector space whose dimension is given by this so-called Riemann-Roch number that did appear in previous talks this week. The Riemann-Roch number involves, first of all, exponent of the symplectic form. So this is a differential form of mixed degree whose integral is just a Villiers-Wheel volume. And the Todd class, this is a characteristic class of a complex vector bundle. So here we are using a choice of compatible, almost complex structure on our symplectic manifold, but the Todd class turns out to be independent of this choice, so it is well defined, and it appears in the formula for the Riemann-Roch number. So right now this is a very formal formula. If you want to actually interpret this as a Hilbert space or a vector space, for example, if you're lucky, but in the many examples this happens, if J is scalar, actually honest to God complex structure, and the higher cohomology of the sheaf of holomorphic section vanishes, in that case, the dimension of the space of holomorphic sections coincides with the Riemann-Roch number. If you only insist that your two form is scalar, but you don't make any assumptions on higher cohomology, you can still get the same Riemann-Roch number. It gives you the dimension of the alternating sum of the sheaf of the cohomology of the sheaf of homomorphic sections. So you're getting a virtual vector space, a formal difference of two vector spaces. In the presence of symmetries, you might have a virtual representation. That's a lot more information. And more generally, if J is almost complex, and that's really the most that you can always do. You can obtain your virtual vector space as a formal difference of kernel and co-kernel of some particular elliptic operator that you cook from the data, and possibly some additional choices. But the answer is always given by the Riemann-Roch number. And now I can state the theorem that I mentioned verbally at the very beginning, that the Riemann-Roch number coincides with the number of integral points in B. And this is interesting because of its interpretation as invariance of polarization, where the left-hand side is interpreted as an index-theoretic quantization using Dirac-Dolbeau operator, and the right-hand side is the Bose-Sommerfeld recipe. So this is why this theorem is interesting. And now I can give you the proof of the theorem. So we have our Lagrangian torus fibration. We've got the pre-quantization line bundle, so that's like a tower. And we will look at V. V is the vertical bundle for the Lagrangian torus fibration. So this is a subbundle of the tangent bundle of M. M is the symplectic manifold. And this is the subbundle consisting of those guys that are tangent to the Lagrangian leaves, Lagrangian tori. And just from this fibration, you get a short exact sequence of vector bundles over M. If you take the tangent bundle to M, mod out by the vertical bundle, that is naturally isomorphic to the pullback of the tangent bundle of the integral affine manifold. And using the symplectic form and the fact that the fibers were Lagrangian, you obtain a natural isomorphism of this vertical bundle with the pullback of the cotangent bundle of B. I hope I said this right. Okay. And the one thing we know is B was integral affine. So the tangent bundle of B is flat. So the cotangent bundle of B is flat. So this guy's flat. On the other hand, you can use any choice of compatible, almost complex structure to identify the tangent space to M with the complexification of the vertical bundle. But the vertical bundle was flat, so the complexification is also flat. So we conclude that the tangent bundle of M is flat. And this is good news, because as soon as you have a flat bundle, then the Todd class becomes trivial. The Riemann-Roch number, whoops, the Riemann-Roch number becomes the Liouville volume. Push it forward, Fubini's theorem gives you the integral affine volume, which through that fact from integral affine geometry coincide with the number of lattice points, which is the number of Bose-Sommerfeld points. And that's it. This concludes the proof, and this concludes my talk. So.
Well, thanks, Yael. So we finished kind of early, so that means we have good time for questions.
Thank you for a nice talk. So this integral affine condition, it's very beautiful, but it's sort of restrictive. So do you see some perspective that a similar fact, or like, for instance, this existence of integral points, can you relax integral and still hope to, like, kind of, is there some perspective that it may work in greater generality?
Well, I mean, you can try to do things. One thing that Mark was doing, which I thought was quite nice, and he has a paper on that, is, you know, let us still assume, like integral is the same as a quantizability condition, right? I mean, one interesting thing, though, is that Mark was taking higher and higher tensors of his pre-quantization line bundle, and then the lattice becomes denser and denser. So this does not answer your question, but it gives you certain sort of feature that leads to some more interesting mathematics.
But yeah, so if you start with an integral, and I think about the lattice, I can rescale the lattice, and the integral will be destroyed. So the question is, do you think if I start with an integral structure, whether I can change it by some simple, by a simple procedure like dilations and maybe a bit more to make it integral?
Okay. If you have an integral affine structure, you can talk, when you look at your tangent bundle as a bundle of vector spaces, and you take like monodromy, that gives you the Dustrumat monodromy, okay? You can do something else. You can look at your tangent bundle as a bundle of affine spaces rather than a bundle of linear spaces. And that guy will have a very natural connection where if you go all the way around, if you go around the loop, the monodromy will live in the affine group rather than the linear group. And the linear part of it is just a Dustrumat monodromy. But there's also an affine part. And this is something called Berger vector in, I've heard about this from people doing material science, like defects in crystals. And so apparently this is something people care about. And this is some sort of global version of sort of a torsion of a connection in some sense. So the Berger vector sort of gives you the obstruction. Like you want that to be integer, to be able to have so there's an obstruction to have an integral affine structure. And if you do have an integral affine structure, if there's no obstruction, then you know how to get all the other ones from, if you have one, all the others one will be just shifts of it.
Yeah, I think what you are describing is what's known as the radius class of the affine structure.
So maybe I know, maybe it's a different name. What is it called?
Radius class?
Oh, then I should talk to you because I'm not, again, I heard about this from people in a different field, but yeah.
But my question was, now I'm allowed to do tricks to your integral affine to make it integral.
I don't know. But this is another thing I should get for you, is the reference for this. What is it called? Radiance?
Well, it's related to the development method.
Yeah, exactly, yes.
Class
Radiance class. No, then I should, yeah. So that's really, absolutely, then I should, yeah, absolutely. So is that take values in sort of, monodromy takes values in affine transformations of, yeah, then I should, yeah. Okay, so.
Is it working? Okay, now it's working. Well, first comment, I think that at least Daniel Sepe, I think calls this integral, I think he calls it strongly integral affine.
Oh, then I should look that up as well,
paper,
because I have enormous trust in everything that Daniele does.
No, I mean, it's just
No, I think that's
just a comment.
Okay. I mean, he's definitely aware of this sort
The question
of
is, if you assume the Marcus conjecture, so if your strongly integral affine is the quotient of Rn by a group of, isn't the proof of this fact much easier?
Possibly.
Isn't it just the number, because you have a fundamental domain?
Possibly. Like if you can, I haven't thought this through, but this is definitely going to be, has a potential of becoming much easier. Like for example, if we know that this guy is finitely covered by torus, then it's going to be much easier.
But I think it's just like you have a fundamental domain, the area of the fundamental domain, or the volume of the fundamental domain is your volume, and you're just saying it's the number.
Oh, you have to be careful, because when you do a fundamental domain, you're going to have boundary contributions.
Right, but you assume that
So-
all integral points are in the interior, which
You have to be cautious with that.
Okay.
So if you want to go through fundamental domains, I don't know. So this requires more thought. That I don't know if you can do. But at least some details of the proofs should become much easier in the special case. Okay, so another thing I'm not entirely clear about is, maybe it's easy, maybe it's hard, is, suppose the universal covering really was Rn, then can you actually find a finite covering that's a torus? I'm not sure. I would need to think about this more. But that would definitely simplify things.
And the other question I have is, did you thought at all about the singular case when
I'm
you
sorry,
have
repeat,
singular
please? I'm
when
sorry.
you have singular Lagrangian fibers?
Yeah,
Singular fibers.
So this will give rise to something a little bit different. So for example, symplectic toric manifold, or Mark Hamilton in his thesis, he was looking at elliptic Lagrangian torus fibrations with elliptic singularities. So you can say things in that case. We were sort of trying to look for the easiest possible case, right? So that's when you don't have boundary. But,
Thank you.
Yeah, so there was a question here.
I just want to make a comment. So maybe this
Okay.
remark of Rui that assuming Marcus conjecture
Yeah.
may simplify the proof a lot, one can look at it like your proof is does support Marcus conjecture, and maybe the tools that you use may be used to prove Marcus conjecture in the integral case.
I would love that to be true. I don't know, I have no idea, but that would be, I find this conjecture very disturbing, right? But that would be wonderful, but I don't know.
So,
Okay.
I've got this one. Thanks. Thank you for a very nice talk. Question. So, still the same story when you think about a quotient. So it's the case when you have a quotient by...
Can you speak slower or louder?
When you have a quotient, the case of a quotient by discrete group. So basically it's one of arithmetic groups, right? So that what it seems is that so first of all, your quantization seems to correspond to choosing some integral cohomology class on the group. So if there is these two pictures, on one picture is quantization, and so finite dimensional thing, which more or less corresponds to constructing some kind of modular forms, and the other one is twisted projective representation of a group, and that's given by some two cohomology class on the group, and you seem to be computing pairing of this class. So computing this class actually.
Computing the?
This cohomology class giving the twisting.
I don't know, but in any case,
the
you
formula
would need
somehow-
some equivariance with respect to your discrete subgroup, right?
Well, it is a quotient, right?
Of course, yeah. So yeah,
By a discrete
I'm
group,
not
right?
sure.
It's really action of discrete group on the domain, right?
Yeah.
It's class, characteristic class for this discrete group. So there is this kind of formula that shows up when you, for example, for SL and Z.
So you're proposing that there's a more general setup where one can one has a certain expression for the. So I'm assuming pre-quantizability, and you're telling me that the examination of the pre-quantizability condition occurs in a more general
Yes.
setup.
Yes.
So yeah, okay, thank you. Okay.
Maybe I have a question myself. Is there some natural notion of refining the lattice from the integral geometry corresponding to like taking tensor pairs?
Yes, so I sort of mentioned that very briefly, but absolutely yes. And there is a paper of Mark Hamilton where he actually uses this to somehow, in some sense, recover the integral affine structure. So yes, when you take tensors of your line bundle, that gives rise to denser and denser lattices in B, absolutely. And you can formulate things such as semi-classical approximations. You can try to do in that language. Absolutely. I think this is a quite interesting direction.
Well, in that spirit, I was wondering if this fact might have some generalizations where instead of just looking at the volume, you might look at integrals of functions and compare to lattice counts.
Yeah, like Euler-Maclaurin type
Euler-Maclaurin.
stuff. Well, I should know, but yeah, I mean, one could, actually, so here's another let me sort of push this in a different direction. So, and this is connecting to some of the other questions, because when you have those of you who are familiar with symplectic toric manifolds, one would be looking at a polytope and integral points in the polytope. And here we have something integral fine with integer points. But you can sort of combine the two things and come up with sort of compact guys with boundary and corners that are compatible with the, and then one can ask, well, okay, so, do you have this type of theory? Do you have like Riemann-Roch formulas? Because in the case of a polytope, like Euler-Maclaurin involved, like Riemann-Roch becomes a meaningful thing over there. And yes, one can try to look for Euler-Maclaurin type formulas, but I don't know, haven't tried. But various pieces of this game, one could try to combine what people know and do for symplectic toric manifold or polytopes and lattice points on the one hand, and these guys on the other hand, and kind of, yeah, definitely. That's a very interesting direction.
Okay, any other questions? If not, let's thank Yael again. Yeah, and as was announced, there are going to be some announcements now, I think starting with Anton.
Thank you. So the conference is over, but Poisson Live very much continues, and one of the aspects, there will be proceedings of the conference, and this time it is the Journal of Geometry and Physics who kindly agreed to have, I'm not quite sure how it's formulated, a special issue or some kind. So there will be possibilities to submit contributions, and I would like to address an invitation to everybody present here or online, to all speakers and participants. So please do submit your Poisson or near Poisson stuff. It is a journal, so it will be refereed, but we look forward to having lots of interesting contributions, perhaps related to the talks of the speakers or to your posters, or just to your recent contributions and thoughts about Poisson geometry. Thank you.
Okay, thank you, Anton. And then Chenchang want to say a few words. Actually, I want to say a few words before Chenchang says, because Yael was so kind to thank the scientific committee, but most of the scientific committee doesn't actually do all that much work. The one person who does a lot of work is the chair of the scientific committee, and that was Chenchang. And please, Chenchang.
Thanks a lot. That's my pleasure. It was a tremendous, it's amazing activity that the local organizer organized, and we all thank you very much for the local organizer. And I announced that the next Poisson is in Italy with Luca. I send the torch.
Yeah, well, there's this little group of people who volunteer to have next Poisson in the south of Italy. Actually, there are some people in Napoli, some people in Salerno. We haven't decided yet, but most probably we will have everything in Napoli, because Napoli is bigger, there's an airport, there are more facilities, so it's easier. So we look forward to see you all in Napoli. We hope we will be able to welcome you all as well as we were welcome here in Madrid. Let's see. Thank you.
It's hard to bypass this event, but I think Lucas will do something. And I actually thank everybody for your participation. Without you, Poisson won't be there. And see you in 2 years in Italy.
And that concludes Poisson. Have a safe trip home.